Good morning. How are you all feeling? Okay, kind of making it. Yeah. Yeah, I know all of this is really crazy, so we'll just have to do the best that we can. I'm hoping my computer will be fine. It's been acting up a little bit the last half an hour or so, but I just taught a class an hour ago and everything was okay. So we'll see. So I'm recording the meeting right now, and when we're done, I'll just have everything posted up on Sakai, so that way you'll see all the notes here. Let's maybe just try this here. Oops. So, okay, can you all see this poll that I have here? All right, so this is just a quick check-in, just to make sure, like, is everything working okay? Are we all kind of on the same page? Can you see me? Can you hear me? So I'll probably try to do a few polls like this just to make sure that everything really is going well. So I'll just wait a little bit more and make sure everybody's tried the poll here. Okay, so if everything's good, then let's go ahead and get started. So I'm going to show some slides here. I don't really know if slides is going to be the best way to go here for the class. So I'm thinking, let's maybe just try it for the first couple of days and see how it goes. If it turns out that slides are just too difficult to follow along, then I'm more than happy to kind of go to a whiteboard and start to write things there. I can't really see all of your faces at once, but if you have any questions about things, feel free to unmute yourself, ask a question. Also, I'm trying to pay attention to the chat window here. So feel free to also just raise your hand, put something there in the chat window, then I'll try my best to answer it. But also you can just interrupt me and just ask a question right away as well. Right. So the plan for today is really to do three things. So one, I wanted to just say a little bit about how we're going to do the class for the rest of the semester. So just some setup in terms of office hours and the homework assignments and the midterm exam. And then next, I wanted to do a review of what we did before we left for the break. So there really isn't going to be any new content here for today's lecture. This is really just to make sure we're all on the same page. I know it's also been a couple of weeks since we've gone over the material, so I figured that a review of what we did might also be a little bit helpful as well. So you can feel free to follow along either with the lecture notes that are posted on Sakai, or I've also posted the slides as well, and you can use either one of those. But again, if you missed any of this, everything's being recorded, so I'll just go ahead and post all of this online. So of course, what we're going to do from here on out is have all of our classes online, and the classes will be at the typical time, 10 a.m. to 11 a.m. Everything's going to be over Zoom. Of course, you'll need to click on the link here to register in order to watch the videos. But I believe after you do it once, you don't have to do it again. So you should be just fine in terms of seeing the classes, joining the classes from here on out. In terms of office hours, I'm also going to try to hold those over Zoom. So it'll be at the same days, the same time, Monday, Wednesday, Friday, 11 in the morning, then also 4 in the afternoon, of course, both Pacific time. You'll also need to click on these links. You don't need to register for these, but you are going to need to click on the links for Zoom. If you have any issues with this, just feel free to send me an email and hopefully it won't be a problem. If you can't make any of these times, just like before, send me an email. I'm happy to meet with you over Zoom, or if there's another way that'll be easier to meet, like over Skype, we can do that too. For the mentor sessions, Suresh is actually here on the call. He's agreed to have the mentor sessions, but in a little bit more time. So it'll be Sundays, Mondays, Tuesdays, and Thursdays. So this will be from 6 to 8 p.m. Pacific time. So I've also listed the link here over Zoom if you wanted to join those virtual mentor sessions. He's also set up a Facebook group if you'd like to join it there, if you want to ask some other questions. But I do want to thank Suresh for being willing to be available at all of these times for you. Let's see, I think somebody else is joined in. Okay. In terms of the homework assignments, all of the due dates have been pushed back for 2 weeks. So I'll say in just a minute what I mean by the dates. Since we are going to upload everything to Sakai, I decided to make the LaTeX files available for all of the assignments. So let me switch over here so I can show you what's on the web, so you can see what we have. So this is just the web browser for Sakai. So you'll see here, let's see, that when you log in, you see something like this. Under resources, you can just take a look at the various homework assignments. You can see that here I do actually have the tech files. If you don't know anything about LaTeX, I would say don't worry about it. This is just for those that do feel a little bit more comfortable teching up their assignments. Also here for Dropbox, feel free to use this as a place where you can upload all of your files. What I've done so far is I've tried to scan in all of the assignments that have been graded that have not been passed back. And I believe that all of them are now in Sakai. If you have any trouble viewing any of those files, please let me know. I know that a few of you have already uploaded homework set number 9, so I believe I have copies of all of those. I do plan to give those to the graders later on this week. And for the midterm exams, I've just uploaded the scans. I have not had a chance to grade the midterms yet, but I do plan to grade them in the next couple of days. So it's just saying that everything that you've turned in so far, hopefully is there in Sakai, and hopefully you'll be able to get copies of all of those. So coming back over here to the homework assignments, here are the new due dates. So I've tried to put all of this in the calendar on Sakai as well, but I wanted to point out a couple of things here. Homework set number 9 is now due this coming Friday. So that's Friday, April 3rd. So again, if you have a homework assignment, just go ahead and upload it to Sakai. If you have any issues, you can send it to me by email. That's perfectly fine as well. I just find a way to put it up there on Sakai. The next assignment after that would be homework set 10, and that'll be due Friday, April 8th. So just keep in mind that the next 2 assignments will be due at the end of this week and then the middle of next week. And please try to upload everything into Sakai. Let's see here. All right, so there's a question here in the chat window. Do I want the assignments to be titled in a specific format? You don't have to. I've tried to put it so that the homework assignments are like, say, number 9, it will be homework assignment number 9, but you don't have to put it that way. I have to figure out how I can get everything to the graders, and I'm not really sure the right way to do this. So I would just say for the moment, you can put everything into Sakai. Whenever anyone uploads something, I can see that. But in terms of me getting it to the graders, I have to figure it all out later. But that's not anything for you all to worry about. So just at the moment, if you have any issues, send it to me by email. If we're able to upload it to Sakai, then that's great. Now I wanted to move on to say, I want to make sure that there aren't any issues with previously graded assignments. Sometimes there's problems with, like, the graders didn't add up all the points correctly, or maybe the grader forgot to grade a certain problem. What I would strongly suggest is that you scan in all of the assignments that you've already gotten back from the graders. That way, if there are any questions about the grading or adding up of the points, then we all have everything in the same place. Of course, you don't have to do this. This is just saying that if there are any issues, then we don't have to worry about, like, you trying to get me a copy of it so I can see it. So I would just say maybe think about scanning in everything that you have now and trying to put all of that there in the Dropbox folder. Again, if you have any issues, just send me an email and I'm happy to help out in that way. So any questions so far? Okay, great. Now, in terms of the problem sets, let's see. There's a question here. If I still have the homework but not the graded copy, should I upload the ungraded homework? That would be fine. Yeah, please upload whatever you have. Like if you have things like PDFs or like a Word document, something where you've already typed it, but it doesn't look like it has the grade on there, that'll be fine as well. Mainly, I just want to make sure that we do have a record of the assignments in case there are any questions that might come up, a few weeks from now. Just trying to really be preventive about it. So in terms of the problem sets, I've decided that there are only going to be a total of 6 problem sets. So I've already posted problem sets 5 and 6 on Sakai, so you can feel free to start working on those. I believe that we almost have enough material where you can start working on those. At least you can start on problem 5. Problem set 6 will need to know some things about Cauchy sequences, but that's what we're going to get to this week. The due dates are April 10th and April 22nd. The plan that I have at the moment is to try to work through maybe a couple of problems every lesson from here on out. So that way we'll start to kind of slowly work through the problems and won't be kind of shocked if everything has to be done at the last minute. The solutions journal will still be due May 15th at the end of the semester. I probably would recommend that you can start to submit some of the things now. Like if you've already done problem set 1, maybe you can submit that now. If you've done problem set 2, submit that now. That way I can go ahead and grade it and get some feedback to you. If you wanted to wait until the 15th, that's perfectly fine as well. But just thinking that it might make more sense to start to turn in some of the sets now so I can start to look over them. I will ask for volunteers for presenting solutions, but it will not be required for a grade. So that 10% or so that I said before as part of like presenting the solutions in class, that I'm totally waiving, because I do realize that not everyone's going to be able to come here to class. Not everyone's going to be able to present over the video. So what I would just say is just for now, I'll ask for volunteers. If no one's able to do it, then I'll present the solutions here in class. It says here, I have a question for seniors. Should we be prepared to submit the solutions journal earlier? Yes. I believe that the seniors are going to have to submit everything probably around the first week of May. So please submit them as soon as you can. So if you've already done problem sets 1 and 2, go ahead, submit those. I can go ahead and start grading those right away. Okay, any questions about the problem sets then? Okay, I'll keep moving here. For the midterms, there's only going to be a second midterm. Unfortunately, this will not have 2 parts like the first one. There is not going to be an in-class part. There's just going to be the take-home part. I will have it posted in a few weeks. I'll probably give you several days to work on it, pretty much like the last midterm. It will be due Monday, April 27th. So I'll probably pass it out that Friday, April 24th, and then it'll just be due back that Monday. So just think of this as it'll be a take-home portion as opposed to an in-class and a take-home portion. And then finally, for the final presentations, here I've also had to move things around. Instead of us doing in-class presentations, everything will be a video presentation. So in the coming weeks, what I'm going to do is ask that you form a group of maybe 2 to 4 individuals and that you pick one topic. Originally, we were going to do several topics, but because we've had to move back the class periods, I'm going to ask that you pick one topic, and the list of topics is there in the syllabus. From there, I'll ask you to create a 20-minute video. So before I was going to ask you to take over the entire class period. Now I'm just asking you to do a 20-minute video. And there, I'll ask that you be prepared to show the video sometime in the last couple of weeks of the class. You can either do a live video, meaning that I'll just basically let you take over the screen and then you can do whatever you want for the 20 minutes, or you can record a video and then here I'll just show it in class for that 20 minutes. So it'll totally be your call, however you would want to do it. And we'll worry about the details of this later as time moves on, but I just wanted to point out that we still are going to do final presentations. There will be videos, and instead of doing several topics, we'll just do one topic. Okay, any questions, comments so far? Okay, all right, great then. So let's maybe start up on the review. So I want to start off with the recap of where we were the Wednesday before spring break. Right, so that Wednesday before, we were starting to go over this idea of convergence sequences and divergence sequences. Right? So let's say that we have an ordered field, such as the real numbers, and I am assuming everything is complete. So we are going to work over, say, the reals as opposed to like the rational numbers. So first of all, remember this concept of the least upper bound and the greatest lower bound. Right, so let's say that we have a non-empty subset that has an upper bound. So one of the concepts of the supremum, so I'll say this here, is that we really want to say not only is it an upper bound, but somehow we want to make sure that we can actually get as close to that upper bound as we can, right? That's what it means to be the least upper bound. So one way to say that is, given epsilon, we can find an element, a sub epsilon, in the set where if I were to go a little bit larger than the bound, so that's this plus epsilon, then I will be greater, then I can find an element, a sub epsilon, where if I add epsilon to that, I'm greater than the set. Right, so you'll kind of remember this from one of the problem sets, but I wanted to emphasize this today because we'll be using this a little bit later. So again, one of the concepts of least upper bound is that it is an upper bound, but if I add a small epsilon to it, to some element in that set, then I'll be greater than that least upper bound. Similarly, there's the concept of greatest lower bound. So say that I have a set B that has a lower bound, then there the concept is, if I were to subtract an epsilon away from some element, then I would have to be less than that greatest lower bound. So again, this is also one of the problem sets, but I wanted to kind of hit this home to really emphasize that this is the concept with the greatest lower bound. So again, if I have some epsilon, then I can find some element b sub epsilon, where if I subtract epsilon from it, then I'm less than that greatest lower bound. Okay, so does this sound okay so far? All right. Next, we then talked about the concept of sequence. So simply put, a sequence just means that we have some collection of elements. We can write them as x sub 0, x sub 1, x sub 2. And with all of these here, what we're trying to do is say that we have a collection of numbers that is indexed by integers, right? So that means that I have these numbers, x1, x2, x3, and the subscript here is my index. So I can keep track of them by this number here, n. We'll say that our sequence converges to a number L if, given epsilon, I can find a delta such that xn minus L is less than epsilon in absolute value whenever n is greater than delta. Right, so again, kind of intuitively what we're saying here is, it's like a game. If epsilon is given, then I can go out far enough in the sequence, that's what I mean by this delta here, I can go out far enough where I'm as close to L as I want to be. Right, so that's what it means to say that we converge. And then once we have that, then we just write this notation here. So the limit as n increases without bound of x sub n equals L. Okay, so that's what it means to say that a sequence converges. Now we can talk about what does it mean for a sequence to diverge, but there's some weird definitions here. So first we'll say that a sequence increases without bound if, given epsilon, we can find a delta so that xn is greater than epsilon whenever our n here is greater than delta. Right, so here what we're saying is that if epsilon is given, so epsilon could be a really, really large number, I can go out far enough in the sequence where my x sub n is larger than that number. Right, so that's what we mean here by saying that it increases without bound. So if you give me epsilon, which might be really, really big, then I can go out far enough in the sequence where I can make it as large as I want. Right? So similarly, if we try to say this here for something like negative infinity, So we'll say that the sequence decreases without bound if, given epsilon, right, so we can make it to be as large as we want, then our x sub n here is going to be really, really negative. So it'll go as far to the left as we want, as long as we're willing to go out far enough in the sequence, right? So that's what we mean by the statement here. So as n increases without bound, our x sub n here gets really, really large as a negative number, right? So it goes all the way to the left as much as we want. So that's what we mean by saying it decreases without bound. And so then, of course, putting these two together, we'll say that a sequence diverges if it either increases or decreases without bound. Right, so if it like goes off to positive infinity or goes off to negative infinity. And then finally, we'll just simply say that the sequence does not converge if it neither converges nor diverges. So we'll talk about this more a little bit later, but this is just saying that we have this concept of converging, diverging, and then does not converge. Okay. And of course, as an example, we said that if we take a look at the sequence here, so x sub n looks like x0 plus nb, then we want to say that this here either increases without bound or decreases without bound as long as b does not equal to 0. So in this case, as long as b does not equal to 0, we have a divergent sequence. Right? So Zentan, I think that you had your hand raised, so you can type it in chat window or say it.
Yeah. You said that the sequence diverges if it either increases or decreases?
Without bound.
Okay. The notes say nor, so that threw me a bit.
Oh, that's a typo, right? It should be an or, no n.
Okay.
Yeah.
Thanks.
That's right. Yeah, either increases or decreases, right? One or the other. Okay, yeah, thanks for that. Okay, any other questions or comments? Okay, all right, let's keep moving on here. So this is just a very quick example to explain what's going on. So let's take a look at this sequence here. I'll write this as L plus this x0 minus L times rho to the n, where L is this weird thing here, this b over 1 minus rho. But the important thing is here, I'm assuming that rho is a number between 0 and 1. So rho could be like 1/2. So here, everything is set up so that when n is equal to 0, I have x0, and then I have x1, x2, so on and so forth. And so I claim that this sequence converges to L. Right, so here's how we would do this. Remember that every proof here really involves 3 parts. So first we have this initialization phase. So what this means is we always just have to write this as just a statement. This is just the boilerplate. You don't really think about it too much. Let epsilon positive be given. Right, just kind of write it down. You don't really think about it very much. Now, what we're going to do is just think a little bit to figure out what should delta be. So one way we could do this is to say, let's maybe just for the moment write something like this. We might want to set this here equal to epsilon. Right, so this would just be our guess for the moment. So again, we know we have this formula for x sub n, right? So we can write this here in terms of rho to the n. So if I take a look at this absolute value, right? So this x delta minus L, right? So I'm just going to set n is equal to delta for the moment. Then I can multiply things out, and I see here that I have a formula in terms of rho to the delta. So we're just going to work backwards, and we'll just solve for delta from this expression here. Right, so again, we're just going to try something. We have no idea if it works. We're just going to try it, see what happens. So if we do this now, then we have a choice for delta, but of course there's a couple of problems. One is, what happens if x0 equals L? Well, if that's the case, we can't take the log of 0. So in the specific case where x0 equals L, there's some problems, right? We can't do anything here. The second thing is, what if we're dealing with a complete field that's not the real numbers? We only really know how to define the logarithm function if we're dealing with the real numbers, right? We can't really do this otherwise. So I'm going to come back to this by the end of the lesson, but I just wanted to point out for right now that these are going to be a couple of issues that we have to be a little bit careful about. That we just can't say, fine, we're just going to choose delta in this way and be done. There's going to be some subtleties. But for the moment, let's just kind of push through and just say, yes, we can do this. So again, for the moment right now, we have our initialization phase. And so we're going to try to move on from there. All right. So the next case is we need to choose a bound. So remember how the statement goes, given epsilon, there exists a delta. Well, we just started by saying given epsilon. Now the second step is we're going to say, let's choose delta. So let's do this here. Let's either choose delta to be 0, in the case where x0 is L, or we can choose the delta that we had on the previous slide if x0 does not equal to L. The point is that we're choosing both cases pretty much so we have this here. Right, it's not exactly right, but that's going to be kind of the intuition. So I'm trying to choose both cases because I want this very specific formula. So now the last part is I have to actually show everything works. Right, so I really have to show now that if n is greater than delta, then we actually do have the inequality. So we're going to break this into two cases. First case, let's say x0 does equal L. So then if I use the formula here, then I easily see that xn has to be L for all n. Right, so if in the first case x0 is L, then xn is always L. So then that means this here, no matter what, is always less than epsilon. So in other words, what we've now shown is that whenever n is greater than delta, then this xn minus L is always less than epsilon. Right? I mean, this is kind of the silly case because there's really nothing to prove, but that's still how the proof here goes. So again, you have to show whenever n is greater than delta, the absolute value xn minus L is less than epsilon. Right, so does that kind of make sense here for the first case? Okay, yeah, and if you do have any questions, feel free to raise your hand. I think I can see everybody's hand here in my chat window. Okay. Now let's do the second case. So let's say that x0 does not equal L. Well, I noticed two things. One, remember that rho is between 0 and 1. So if I raise that to any natural number, then I get back something less than 1. So think of this as like 1/2. What if I take 1/2, raise that to the first power? If I square it, if I cube it, take 1/2, raise it to any number that's a positive integer, then it's always going to be less than 1. Right? So that's what this part here says. Right? If I take a number less than 1 and raise it to any integer that's positive, then it's always less than 1. So I'm going to use this now to say if I take a look at xn minus L, then I know that I have this formula here that says I can write this in terms of rho to the n. But now, remember how I chose my delta, right? That this thing here is going to be equal to epsilon. So I put all of this to say that whenever n is greater than delta, this absolute value here is less than epsilon. And that's exactly what we want in order to say that we have a limit. Right, so again, whenever n is greater than delta, this absolute value, xn minus L, is less than epsilon. Okay, all right, any questions here on the second case? Right. So now we can just put all of this together to say that this is just what we've shown. So this is just kind of the boilerplate to finish off the proof. Given epsilon is positive, I can find a delta such that whenever n is greater than delta, the absolute value here is less than epsilon, but that is by definition the same thing saying that the limit here is L. All right, so again, this is just kind of saying this is the end of the proof. All right. Now, I want to give an aside here. This is for those that really remember all of these details from when we did this the Friday before spring break. This is not going to be needed really on like the homework or anything. This is just kind of an aside to just ask a very basic question. Do we really need to have these different definitions of convergence and then increasing without bound and decreasing without bound? Is there a way I can put all of this together into one coherent definition? So say that we have a sequence. And remember that if I stay away from the case of does not converge, we said that there are three cases. Either the limit is some number L, or it increases without bound, or it decreases without bound. Right? Those we said were the three cases. So of course, in the first case, this is what it means to converge. And then in the other two cases, this is what it means to diverge. Right? So I just want to ask a simple question. Can I really put all of this into one definition as opposed to saying that I have these three? To do this, I'm going to introduce a really weird concept. So I want to say, if you were to give me a number t, so this might be a real number, I'm going to plot that on the unit circle. All right, so again, if you give me a number t, I'm going to plot that onto the unit circle. And conversely, if you were to give me a point on the unit circle, I'm going to write down this number here, t. Right. So there's a question, are these cases for converge or does not converge? What this says is, let's stay away from does not converge. So if I do that, then I really have three cases. Either it converges, it increases without bound, or it decreases without bound. So what I want to ask is, if I have these three cases, can I put all of that into one definition? Yes, this mapping is bijective. So bijective means if you give me a t, I can give you back an x and y. And conversely, if you give me an x and y, I give you back a t. So this is a one-to-one correspondence. So whenever I think of a number in f, I can also think of that as the point here, x comma y. And conversely, if you give me a point x comma y, I can write down this number here, t. Right? So I want to identify f here as the unit circle. So let me kind of draw a picture so I can show you here, here's what's happening. So this circle here is quite literally the unit circle. So x squared plus y squared equals 1. This line here is the line going through the point 0, -1 that has slope t. So what I'm saying here is, if you give me t, I will draw a line of slope t. That will intersect here at this point that I was calling xy. So that's exactly this formula here. Conversely, if you give me this point here, xy, I'm going to intersect that through the second point, and then that'll give me here this line that kind of goes through those two. All right, so again, if you give me 2 points here on the unit circle, then I can give you back the slope here of that line. So I want to think of this as I have a t that ranges all the way up and down here, the real axis, then that should correspond here to this line. So in some sense, I'm kind of wrapping the real line around the circle. All right, so take this infinite line here, and I'm going to try my best to kind of wrap it around onto the circle. So there's a question, how does this mapping relate to converting the complex plane into the Riemann sphere? This is actually what's called stereographic projection. So for those of you who've taken a little bit of complex analysis, this here is stereographic projection. I'm just not writing it in the fancy way here because we don't really need all of that, but that's essentially all that we're doing here. Okay. So let me now try to explain, how does this relate to sequences? So if I'm given an element in the sequence, call it t sub n, I can write down a point on the circle. So that means if I take a look at 2 points on the circle, I can look at how far apart are they. And there's just the formula that goes like this here. I would say don't really worry about this formula too much, because all that it says is if I'm given a couple of points in the sequence, call them t sub n, I can write down a couple of points on the circle. And the simple statement is these 2 points are very close together if and only if I have 2 elements in the sequence that are very close together. But of course, that should make sense. So if the sequence looks like they're kind of getting very close together, then the points on the circle should be getting very close together. Here's the part that's surprising. Infinity actually corresponds to the North Pole, right? So what does it mean to say that I have a line of infinite slope? Well, that just means it's a vertical line. But a vertical line just means that it's going to intersect at the North Pole. It's going to be kind of at the very top. So I can look at now the difference between a point in my sequence and the North Pole. So I have a formula here. And again, I would say don't worry about the formula too much. The statement is that I have this here. This difference, Pn minus the North Pole, is small if and only if Tn is large. So the whole point here is that if Tn increases without bound, or if Tn decreases without bound, then I'm getting very, very close to the North Pole. So again, if I'm increasing or decreasing without bound, then it looks like my sequence is getting very, very close to the North Pole. So I'm going to put all this together to make the following definition. I'm going to say that my sequence converges if and only if, given epsilon, this difference in the points on the circle are very close whenever m and n are large enough. Notice that this keeps track of convergence in the usual sense, as well as increases without bound, as well as decreases without bound. So this actually takes care of all 3 cases at once. So all that we're saying here is move over to the unit circle, and then you can actually make your definitions. Similarly, we'll say that our sequence does not converge if we have otherwise. Right, so again, I want to try to come back to this concept a little bit later. If this doesn't make a whole lot of sense, I would say don't stress out over it now. This is just saying that there is a way we can take this idea of divergence, that is increase without bound, decrease without bound, and we can put it into all one coherent definition. So there really aren't 3 definitions. There really is just one definition if we set up everything in the right way. Okay, does all this make a little bit of sense so far? Okay, let's try to move on here. So I want to go over next about this concept of monotone sequences. So we really had just a few ideas based on the following concept. Well, let's go back to the previous example where we had the exabends, let's say, defined in this way here. And remember that we proved before that the sequence tends to a limit. And the way that we did this was by trying to find our delta. We had to introduce the logarithm function, but of course we can't do this for any complete field, so we have to be a little bit careful. So what I want to know is, can I prove that the sequence converges to L for any complete order field? Right, that's the motivation. Can I do this without reducing to the logarithm function? Right, so it all comes down to the following identity, that if we take a look at this absolute value, we could write everything in terms of this here. And then the whole point here was that we really wanted to state the following. If rho is between 0 and 1, so like maybe rho is 1/2, can I raise rho to a power and make it as small as I want? So if I have something like a half, then I always have like a 1/4, an 1/8, a 1/16. I can always raise it to a power to make it smaller and smaller. But the question now is, can I maybe just use my axioms to prove that I can always raise it to a power to make it small? Right, so this is without using the logarithm function. So the question is, can I always do this? And so we're going to prove a theorem to prove that the answer is yes. You can always do this. So of course, I want to make this following observation, that I actually have a decreasing sequence of numbers. Of course, if rho is less than 1, then rho squared is less than rho cubed is less than rho squared, So I do have now a decreasing sequence, right? So that's going to be the concept that we'll try to introduce next. Simply put, we'll say that a sequence is monotone increasing if xn plus 1 is greater than or equal to xn. We'll say that our sequence is monotone decreasing if xn plus 1 is less than or equal to xn. And we'll just say that our sequence is monotone if it's either monotone increasing or monotone decreasing. Right, so just one of those three. So either one of those two, either monotone increasing or monotone decreasing. So there is a main theorem that we want to prove when it comes to monotone sequences. It's what's called the monotone convergence theorem. So as a reminder, we'll say that it's monotone increasing if we have the statement here about xn plus 1 and xn, and we'll say that it's monotone decreasing if we have the statement here about xn plus 1 and xn. So if we have a monotone sequence, then we have two statements. Number one, if it's monotone increasing with an upper bound, then the sequence converges. Otherwise, if it's monotone increasing and it doesn't have an upper bound, then the sequence increases without bound. Right. Second part of the statement is, if we have a monotone decreasing sequence that has a lower bound, then the sequence converges. If we have a monotone decreasing sequence with no lower bound, then the sequence decreases without bound. So the sequence diverges. Right? So again, this is the monotone convergence theorem. So it says that if it's monotone increasing, either it converges to something or it increases without bound. If it's decreasing, it's something similar. Either it converges or decreases without bound. Right, we always have one of these two. Okay. So what I'd like to do is go over the proof of this theorem here. And what we're going to do is really break up into 4 cases. So either it's increasing, it has a bound or it doesn't. It's decreasing, it has a bound or it doesn't. But all of this here is just going to be an exercise in kind of those 3 steps, right? So say epsilon is given, choose a delta, show that everything works. So we're just going to do those 3 steps over and over again. So let's start with the first case. All right, let's assume that we have a monotone increasing sequence. So again, we have 2 cases to focus on. First, let's say that we do have an upper bound. And of course, if we have an upper bound, it's a non-empty set because it's a sequence. So it has a least upper bound. So we'll call this least upper bound L. We're going to prove that xn converges to L. Right? That'll be the first of the 4 cases. So of course, we'll always start with this boilerplate. We'll always just say, let epsilon be given. Right? You don't really think about it, you just say it right away. Now, we have to show what is delta. So here's where I'm going to use the statement that I made earlier about least upper bounds. Right, so remember that I stated at the very start of the lesson today that least upper bound means I can find something in the set where if I just increase it a little bit by epsilon, then I'm greater than that least upper bound. Right, so again, this is what was in one of the problem sets, but this was the idea of what a least upper bound is. So if I have an epsilon, then there's some element in that set, call it x sub delta, where if I add epsilon to that, then I should be greater than the least upper bound. Right? So that's now going to be my delta. So now we'll do the next boilerplate. Say that any n is greater than delta, so we have to prove that everything works out in the right way. So here's going to be our argument. So first, let's start with this statement here. Right, let's take a look at xn minus L in absolute value. Well, because xn is less than or equal to L, where L is an upper bound, then the absolute value has to be this here. Right, because I have to worry about whether I want the positive or negative one. In this case, of course, I do want the positive one. Now, I know that we have an increasing sequence. So as long as n is greater than delta, x sub n is greater than x sub delta. Right, so again, as long as n is greater than delta, x sub n is greater than x sub delta. So that's why we have this here has to be less than this here. Right, because again, x sub n is greater than x sub delta. Okay. And so then finally, we just recall by the definition of least upper bound that this quantity here has to be less than epsilon. Right, because again, that was the whole concept of what do we mean by least upper bound. Okay. So any questions on how we have these inequalities? Right. So then putting all that together, then we see that the convergence, the sequence here has to converge to L, right? So that's the very first case. Okay, let's keep moving on here. So now let's do the second part. Let's say that A does not have an upper bound. Right? So again, we'll just do three cases. So here's our, or I should say 3 steps. So here's our boilerplate. Say the epsilon is given. Well, we can find a delta so that we have this case here. X sub delta is greater than epsilon. This is because A doesn't have an upper bound. Right, so that means I can go far enough out in the sequence where then I'm greater than epsilon. If this were not true, if I could not find such a delta, then epsilon would be an upper bound for the set A. Right, so simply put, this does say that I can go out far enough where then I'm greater than whatever bound you possibly want. So now, we just kind of put everything together. Well, because we have an increasing sequence, then xn is greater than x delta. And if this is the case here, then xn has to be greater than epsilon. Right? But of course, that's just exactly what it means by definition to say that it increases without bound. Right? Okay, any questions so far? Okay, let's maybe take a quick break for a second. I'm going to try to set up another poll. And let's just see, does all of this make sense? So I'm just have a poll real quick here. Just take a quick break. Make sure we're all on the same page. So I'm just asking right now, you follow me? Is this kind of a little bit too much? And it is an anonymous poll, so you don't have to worry about whether your name will be attached to it. Okay, so that looks good. So yeah, so if half the class is confused, that's fine. That's definitely fine. So let's maybe kind of slow down a little bit. I do want to try to finish off the proof here. If there are things that don't make any sense, just feel free to either put it in the chat window, speak up and say something, raise your hand. Either one of those would be perfectly fine. But certainly if there's something that doesn't make any sense, then I do want to try to slow down and go over this again. Okay, so let's try to do this. I'm going to try to do the proof here for the next case. So let's do the second case here. Right, so this is the case where A is a monotone decreasing sequence. Right? So in this case, remember that we have two possibilities. Either it's bounded or it's not. So let's say that we have a lower bound. Right, so we're going to do almost the same proof as before, but we'll move things around just a little bit. So if it has a lower bound, we have a sequence. So that means it's a non-empty set. So then it has a greatest lower bound. So we're going to call that the infimum. Right? So if we have an infimum, we're going to try to do the same thing as before. We're going to try to prove that this sequence tends to L. Right? So this should be our limit. So same three cases as before. So let's say the epsilon is given. Right? Now, because we have a least upper bound, we're going to write this trick here of what is the definition of least upper bound. So this says, of course, that it has to be, greatest lower bound. So it has to be a lower bound, but the whole point of greatest lower bound means that if I try to subtract away epsilon, so if I try to get just a little bit less, then that means I can find an element where I'm going to be now less than that lower bound. Right, so again, the whole point here is that I should be able to find some element in my set, which I'm calling x sub delta, where if I subtract just a little bit, subtract an epsilon, then I'll be less than that lower bound. All right, so again, this was what was in one of the problem sets. So I do want to say that I can find a delta so that I have this x delta in my sequence. So now we can finish off the proof. So let's pick an n greater than delta. And now we'll just try to work out the same proof as before. So I do want to consider this absolute value, right? Xn minus L. So I know that that absolute value is equal to this because, of course, Xn is greater than L, right? L is a lower bound. So we have this here. We'll pick this as our absolute value. Now we have a decreasing sequence. So in other words, Xn is less than x delta. So again, delta is less than n, so xn has to be less than x delta. But that's exactly the same as saying this here, right? That xn is less than x delta. I have a decreasing sequence. Okay. So then this here has to be less than epsilon because of the way that we set up greatest lower bound. All right, so I know that this here has to be less than epsilon because of the way we set up our greatest lower bound. Okay. So then finally putting all of that together, then we see here that the sequence has to converge to L. Okay. So one of the questions asked is that we have here this x delta minus epsilon is less than L. Does it matter what the subscript is? It actually does matter, very crucially. So the subscript, when I write here x delta, this is because it is an element from A. Right, so remember that the elements A look like x0, x1, x2, all the rest of those. So x delta means that it's an element from A. So that delta is because we have a sequence, and our sequence looks like it's indexed by these subscripts. So that delta is part of the subscript that really reminds me that it's from A. Right, so I don't really want to say x sub epsilon. I really want to say x sub delta. Because the delta is telling me, do I want it to be x0? Do I want it to be x5? I need to figure out which one of the x sub n's do I really want. Okay, any other questions? Okay. All right, so this is the third case. So now we can do the last case and kind of finish everything off here. So let's say that A does not have a lower bound. So we're going to do the proof almost the same as before. So we'll start with our boilerplate, let epsilon be given. Now we have to choose delta. So in this case, I can find an element in the sequence that's less than negative epsilon. This is because A does not have a lower bound. If A did have a lower bound, then we could not do this. Right, so the whole point here is that I can always find an element in the sequence, some x sub delta in A, that's less than negative epsilon. If this were not true, then negative epsilon will be a lower bound. Right, so it just says that I can always go far enough out in the sequence where I can now go to the left of negative epsilon. Okay. So now we just finish off the proof. Well, we have a decreasing sequence. So as long as n is greater than delta, then x sub n is less than x sub delta. Right, so that's what we say here. As long as n is less than delta, sorry, greater than delta, then x sub n is less than x sub delta. But I do know that other people have to go in just a couple of minutes, so we'll finish up here in another minute or so. So now we just put everything together, and we realize that our x sub n is less than negative epsilon, right? And of course, that's exactly what we wanted to show, that our sequence does decrease without bound. Okay, all right, any questions so far? Okay, so let's just try to finish off things with just a couple of examples. So I'm going to come back to this sequence that we started things off with. This x sub n looks like x0 plus nb, where b does not equal to 0. Well, if we do the trick here of placing this as a sequence, we see that either it's monotone increasing or monotone decreasing, depending upon whether b is positive or negative. So we have a monotone sequence. We've already seen that this sequence diverges, right? Either it increases without bound or decreases without bound. Right. Let's take a look at this other sequence here, right? So this whole thing that we started the class with, where rho here is between 0 and 1. I'm going to prove that this converges to L by introducing a new sequence. So let's call this T sub n to be this new sequence here. So we see actually that this is a decreasing sequence. And actually it has a lower bound, right? Everything here has to be non-negative. And you can actually prove that the infimum of this set is 0. Right, so if I have the sequence here, its infimum is 0. So I'm not going to worry about proving that. So the point here is that now I just use the monotone convergence theorem to say, well, this sequence T sub n goes to 0. Therefore, I can say that here, this is less than epsilon. Right, that's the crucial part here. I really want to say that I can find the delta so that if n is greater than delta, then this thing here is less than epsilon. Right, but of course, that's exactly what we wanted to show. Right, so this actually gives a different way of proving that this sequence converges to L without using logarithms, without using anything else that's really fancy. Okay, so I'll just end here just by recapping that here we're just using the monotone convergence theorem. We're going to try our best to use this again as the course continues. Right, so know that everyone does have to go here. So I'll be around in case you do have any more questions, but remember that I do have office hours from here on out. So thank you all for coming to class today, and we'll try this again on Wednesday. Okay, any questions while we're still here for the next few minutes? Okay, all right, well, thanks for coming then. So I'm going to close out the meeting here, but then I'll be around for office hours in case you have any questions there. All right, so see you on Wednesday.